In the second part of the lecture, we will discuss spectral clustering. This is the moon's dataset that can be simulated in scikit-learn. It consists of two well-separated moon-shaped clusters. But the question is, would K-means clustering or a Gaussian mixture clustering be able to identify these two clusters correctly? So let's have a look. And from these results, you see that these two methods struggle to identify the clusters correctly. And this is obviously due to the shape of the clusters and highly nonlinear boundary that is required for this example. And this is where spectral clustering becomes useful. Spectral clustering performs nonlinear manifold embedding, such as Laplacian eigenmap that you learned about in this module, followed by K-means clustering most commonly. And you can see that for this example, spectral clustering perfectly identified these two clusters. So let's see why spectral clustering works for this example. So spectral clustering builds on Laplacian eigenmap that you already know and are familiar with, but I will recap the main steps. So in the first step, we create a symmetric K nearest neighbor graph to define the affinity matrix. And in this example, we used K equals to 5. So for each point, we find the K nearest neighbors and join them with the edge to this point. This K nearest neighbor graph is also symmetrized after. And you see that for this example, this graph resulted in two connected components, and therefore it separated the data set correctly. So then what follows, we calculate the graph Laplacian and its eigenvalues and eigenvectors. Then we order the eigenvalues from smallest to largest, and the eigenvectors corresponding to a predefined number of smallest eigenvalues, except for the first one, will form the new embedded space. The final step is to perform K-means clustering on the embedded space. Important theoretical fact to realize is that graph Laplacian has exactly 1 zero eigenvalue for each connected component. For this reason, the first eigenvalue is always 0 because we always have at least one connected component, and the corresponding eigenvector is excluded from the embedded feature space because it's not informative. So if we look at our moon's example, we obviously have two connected components, so there will be two zero eigenvalues of graph Laplacian, and one of them will be excluded. So the first embedded dimension will also correspond to zero eigenvalue. And if we look at this dimension in this plot, so on x-axis, we have the sample index, so that's all our samples from 0 to 100. And on y-axis, we have the first embedded feature. We can see that there are only two discrete values of the first feature. So each sample gets either one or the other discrete value. So we can see that this first dimension directly defines these two disconnected components of the graph. So when the clusters are disconnected, the data set falls into several discrete feature points in the embedded space. Here is the embedding plotted in 3D. So we took first 3 embedded features. And you can see that the first feature defines the 2 clusters. The second feature is a one-dimensional representation of the red cluster. And the third feature is one-dimensional representation of the blue cluster. And we can also visualize that in the original Euclidean space if we color code the samples by their embedded features. So if we color code them by feature 1, we see the two clusters. So the two moons were separated by feature 1. Then feature 2 represents the one-dimensional embedding of the bottom moon. So it varies from one side of the moon to the other, and in the other moon is constant, and the feature 3 varies alongside the top moon, and in the bottom moon is constant. So we see how this embedding directly defines the two clusters. So, so far we only use symmetric k-nearest neighbor graph to create the affinity matrix, but there are other choices that we can make. So if we do have distances, for example, Euclidean distances on the feature vectors, we can use Gaussian kernel to convert them to similarities and that way design the matrix A. Or we can also use other types of similarities. For example, we could use normalized cross-correlation between feature vectors. This is useful when it is difficult to define a distance. So far, we used unnormalized graph Laplacian, and this works well when the degrees of the nodes are similar. So obviously, for a k-nearest neighbor graph, the degrees will be approximately k. So that's why it works well. But if the degrees vary, it's better to normalize the graph Laplacian. And that can be done by multiplying it by inverse of the degree matrix D. And there you see here two different versions of doing that. So in scikit-learn, there is an object called spectral clustering that implements this spectral clustering. We have three options for affinity. There is k-nearest neighbor affinity. That is the one you are familiar with. And we set it by parameter affinity equals to nearest neighbors. And in this case, we will feed directly the feature vector because this object will then calculate the Euclidean distances and the resulting KNN symmetrized graph and the affinity matrix. Alternative is to use Gaussian kernel to create the affinity matrix. Here we again feed the feature matrix X, then Euclidean distances are calculated and converted to affinities with Gaussian kernel. And there is an option as well for the affinity matrix to be pre-computed by the user. And in this case, we will feed directly the pre-computed affinity matrix rather than the feature vector to the model. And scikit-learn uses normalized graph Laplacian in all cases. So finally, let's have a look at an example where we need to pre-compute the affinity matrix because Euclidean distances don't exist. So a question that we ask, can we cluster directly brain MRI of term and preterm babies can at the term equivalent age? So how would we go about that? So first thing we need to think about how do we construct this affinity matrix. And one way to do that is to align all the images to the same reference space and then calculate normalized cross-correlation between pairs of aligned images. So this cross-correlation, of course, is calculated for all the voxels in the image. And because we have images with the same contrast, it will be always positive, but it will be never larger than 1, because if we do cross-correlation of an image with itself, we will get 1. So we see from that we will have fully connected graph. And we will use normalized graph Laplacian for this case because the degrees of the nodes may vary. And experimentally, we will choose 3D embedding with 3 clusters. And here you can see the result. We plotted the first and second embedded feature and the resulting 3 clusters. So if we then color code the embedded data points by age at birth, we can actually see that this cluster of green triangles, which is cluster 3, corresponds to preterm babies, which is quite interesting. So to visualize the features that spectral clustering learned in this example, we can calculate the average images for each cluster. And in this case, because we see that cluster 1 and 2 correspond to term babies and there doesn't seem to be a particular dependence on the gestational age at birth, we join them together and calculate the average image for these 2 clusters. And then we also calculate average image for cluster 3 that mostly corresponds to preterm babies. And here we can see the most obvious difference, that there is more cerebrospinal fluid in cluster 3. And this is a common feature that results from preterm birth. And one interesting sample that we can look at is this one, because it's clearly within the preterm cluster, but actually this is not a preterm baby, this is a baby born on time. And we can see that this baby nevertheless has more a CSF, just like the preterm baby. So that's probably the reason why it ended up in preterm cluster. So this is the end of the clustering lecture. In the tutorial, there are 2 Jupyter notebooks, Gaussian mixture and spectral clustering, where you can practice clustering in scikit-learn. There is also an optional tutorial resource where you will implement your own k-means clustering algorithm for 2 classes or 2 clusters. There is a skeleton Jupyter code on kids that you can complete in a Spider editor. And solved notebooks and code are also available on kids. So now is the time to test your knowledge on spectral clustering, which you will do using a quiz on kids. And when you are done, please move on to the lecture on feature selection.